Let's now look at the energy budget of a simple circuit, one containing each of the circuit elements that we've discussed. So here, our system will be the entire circuit. Everything will be inside the system here. There will be no external fields to worry about. In our system, we have three energy storage devices. The battery stores energy in the form of chemical potential energy. The inductor stores energy in the magnetic field that is generated inside those coils when the current is flowing. So when there is current generating a B field inside that solenoid, there's energy stored in the field itself in the seemingly empty space inside that coil. Energy is being stored because there is B field there, as we showed. This is the density of energy inside the coil, given that there's some B field in the coil because there's current flowing through the coil. Likewise, in our capacitor, it stores energy in the electric field between the plates when the plates are charged. So in the empty space between the plates, the seemingly empty space, there's energy stored in that space if there's E field in that space. And the magnitude of the E field corresponds to the density of the energy stored in the seemingly empty space between those plates. So our inductor is storing energy in the B field. Our capacitor stores energy in an E field. Two different devices that both store energy in the fields. Your resistor, here's the one thing that's going to be converting your stored energy into a non-mechanical form, into heat. Your resistor is dissipating energy as heat whenever current flows through it, no matter the direction of the current or the rate, no matter the direction of the current, as long as current is flowing, as long as current is non-zero, that resistor is going to be causing some energy loss, some dissipation as heat. So if we're going to do some accounting for the total energy of our system, we could say it comes in these forms: the potential energy stored in the battery, the potential energy stored in the B field in your conductor, the potential energy stored in the E field in your capacitor, and the total kinetic energy of all the thermal motions of all the electrons bouncing around, the total kinetic energy of all the motions of the electrons inside your wires. When we look at changes in the energy of the system, say when we flip a switch and allow current to flow one direction or another, when we look at changes in the energy of our circuit, we can draw energy out of our battery or add energy to the battery. We could add energy to or from our inductor by changing the current through here. We could add energy to or from our capacitor by charging or discharging our capacitor. But as we've discussed before, the current does very little to change the kinetic energy of all the random motions of the electrons in the wire. Their motions are still mostly random, and the tiny drift velocity that they get from participating in current is a negligible contribution, negligible change to the total kinetic energy. So we can neglect that in our circuit. But these three components can exchange energy with one another. And your resistor here, that's the one component that can potentially remove energy from the system. Your resistor is the thing that can do some applied work on the system. That would be an internal, non-conservative force, your dissipative force inside this resistor, doing non-conservative work, converting this energy into heat. So the work done by this resistor, this is always going to be negative work, reducing the energy of the system whenever current is flowing. So more explicitly, we could say that the change in the energy being stored in the inductor is due to a change in this expression. So it depends on the current that's flowing. So changes in the current will result in changes in energy stored here. Likewise, in your capacitor, changes in the charge on your plates. The changes in the charge result in changes in the energy stored here. And we can write this expression for the work being done by the resistor over some amount of time. This is the power output of your resistor. From Ohm's law, power is I squared R, and a resistor of resistance R right here. So power, I squared R, integrated over time, gives you the total energy dissipated as heat over some time interval, from a starting time 1 to a final time 2. And that is, of course, negative. That's a loss of energy to the system. One more way of expressing that, to once again emphasize the idea that potential energy is stored in the fields, would be to write these two expressions like this. So our battery can change in the stored potential energy that it has. The energy being stored in the inductor can change if the magnetic field strength squared changes. It's the field that stores energy, the B field, the magnetic field, storing energy inside the coils of the inductor. And in our capacitor, a change in the E field strength squared between the plates results in a change in the energy stored, because it's the E field in between the plates that is storing the energy that the capacitor is storing.